This next example was from the 2011 BCE free response question number 6. Okay, and it's let f of x equals sine of x squared plus cosine of x, and then the graph of y equals the absolute value of the fifth derivative of x is shown above. So this is the absolute value of the fifth derivative graph. Okay, and then write the first four non-zero terms of the Taylor series for sine x about x equals 0. So centered at x equals 0, and then write the first four non-zero terms of the Taylor series for sine of x squared about x equals 0, okay? So we know that sine of x can be approximated by a Taylor series, so this needs to be an approximation, not an equal, okay? And it's x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, and then minus x to the seventh over 7 factorial. And that's the first four non-zero terms, okay? So then we need to use that to pick up the sine of x squared. So sine of x squared can be approximated by putting x squared everywhere you see x, okay? So just substituting x squared for all of these x's, okay? So this would be x squared, and then minus, and then it would be x squared cubed over 3 factorial, and then plus x squared to the fifth over 5 factorial, and then minus x squared to the seventh over 7 factorial. And then that would be approximately, so sine of x squared would be approximately x squared minus x to the sixth over 3 factorial plus x to the 10th over 5 factorial, and then minus x to the 14th over 7 factorial, okay? And that would be the first four non-zero terms for both sine x and for sine of x squared. All right, for part B, we want to write the first four non-zero terms of the Taylor series for cosine x about x equals 0. And then we want to use the series and the series for sine of x squared found in part A, that's what we just did up here, okay, to write the first four non-zero terms of the Taylor series. And I forgot to, this is a typo, okay, for f, okay, for f about x equals 0. So we're going to write a Taylor series for that original function that's up above, that's sine of x squared plus cosine of x, okay? So let's start by doing this cosine x, okay? So cosine x is approximately, okay, and it would be 1 and then minus x squared over 2 factorial plus x to the fourth over 4 factorial, and then minus x to the sixth over 6 factorial, okay? Now this coefficient for x squared is 1 over 2 factorial. The coefficient for x to the fourth is 1 over 4 factorial, okay? And so now what we want to do is f of x, okay? So we have f of x, which is equal to sine of x squared plus cosine of x, okay? And that can be approximated, okay? So f of x can be approximated, okay, with adding these two Taylor polynomials, these first four non-zeros together, okay? So you want to look at sine of x squared, okay, and cosine x, and do you have any constants? And you do, you have this 1, okay? So let's put that, all right? And then what we want to do next is look for x squared terms, okay? Or not, I'm sorry, x terms. And sine of x squared doesn't have any x terms. Cosine x doesn't have any x terms, okay? So there's no coefficient that we can put together there, okay? And then we need x squared, okay? So sine of x squared has 1x squared, and cosine x has a negative x squared over 2 factorial, okay? So we're going to add, okay? And it's going to be these two coefficients. So it's going to be 1, and this one's negative, so negative 1 over 2 factorial times x squared. Because if you distribute this, it would give you the x squared, and it would give you the negative x squared over 2 factorial, okay? All right, so now we're looking for x cubed. So x, so that's this, so we have two terms here, okay? Now, this looks like two terms right here, but it's not, it's one, because that's just the coefficient for x squared, okay? And so then we need to look for x cubed. Well, we don't have x cubed, right? We don't have any of those, okay? So then do we have an x to the fourth? And we do, it's right here, okay? All right, so then we need to add, do 1 over 4 factorial x to the fourth. Okay, so now we have 1, 2, 3 terms. Okay, so we have basically x to the 0 term, x squared term, x to the fourth term. So then we're looking for x to the fifth, and we don't have x to the fifth in sine x squared. We don't have x to the fifth in cosine x. So now we look to x to the sixth. Okay, so x to the sixth, we have negative 1 over 3 factorial. And over here for cosine x, we have negative 1 over 6 factorial. So I'm going to add, okay, those two coefficients. So it'd be negative 1 over 3 factorial. And then, yeah, negative 1 over 3 factorial. And then for cosine x, it's going to be negative 1 over 6 factorial. And then times that by x to the 6th power. So this would give you the first 4 non-zero terms for f of x. All right, for part C on this problem, we want to find the value of the 6th derivative at 0, okay? So they don't expect you to go through and do all the derivatives, okay? What they want you to realize is that f, the 6th derivative at 0 over 6 factorial times x to the 6th, that's a term in the Taylor polynomial, right? And so you can get derivatives from looking at the coefficients for a Taylor polynomial, okay? So what we know from part B, okay, from what we just did, I'm going to grab my paper. We know that the coefficient for x to the 6th is this, okay? So I know that this f, the 6th derivative of f at 0 over 6 factorial is equivalent to, and I'm going to use parentheses here, so negative 1 over 3 factorial minus 1 over 6 factorial. Okay, that's the coefficient. So that, and then times x to the 6th. So the 6th derivative at 0 over 6 factorial is this number right here. Okay, so I'm going to write this so it's the 6th derivative at 0 over 6 factorial. We know that must equal negative 1 over 3 factorial minus 1 over 6 factorial. Those have to be the same. So I'm going to multiply both sides because this is an equation. So I'm going to multiply both sides by 6 factorial, and that will give me the 6th derivative. Okay, so this would be negative 1 over 3 factorial minus 1 over 6 factorial times 6 factorial, okay? And then that means the 6th derivative at 0 would be negative 6 factorial over 3 factorial minus 6 factorial over 6 factorial, okay? So that means the 6th derivative, of course, I have to go further, right? You could stop right here and that would be your answer, okay, on the AP exam. Okay, so this would be negative, and this would be 6 times 5 times 4, and we wouldn't go all the way down to 3 because the 3, 2, 1, 3 times 2 times 1 are going to cancel. So this is negative, okay, and then 5 times 4 times, I'm sorry, not 5, 6. Let me get my white out. Okay, so this would be 6 times 5 times 4, and 3 on down would cancel, okay? And then this would be minus 1, okay? So the 6th derivative at 0 would be equal to negative, and then 6 times 5 is 30, and 30 times 4 is 120, so this is 120 minus 1. So that means the 6th derivative at 0 would be negative 121. Okay? All right, so for part D, we're going to let the fourth order or fourth degree Taylor polynomial be the fourth degree Taylor polynomial for f about x equals 0. Use the information from the graph of y equals the absolute value of the fifth derivative of x shown above. Okay, so that's from the first page, and show that the this is the error, right? Because this is the fourth degree Taylor polynomial at 1/4 minus the function at 1/4. That's the error. And we want to show that that error is less than 1 over 3,000, okay? So we're going to use that Lagrange error bound to show this, okay? So here we go. So we're going to take the absolute value of, let me get a different pen. Okay, so the absolute value of the fourth degree or fourth order at 1/4 minus f of 1/4. Okay, so we know that that is equivalent to the absolute value of the remainder, okay, for the fourth order Taylor polynomial at 1/4. Okay, and then we know that this has to be equal to the absolute value of, remember there's a n plus 1 derivative, okay, so that'd be the fifth derivative, right? That's where the graph is going to come in at some value c, okay, at some value c over 5 factorial times, in this case, we're putting 1/4 in for x, so it's going to be 1/4 raised to the fifth power. Okay, now from Lagrange error bound, we know that that this, if we find the maximum of this, right, then that's going to be less, this error is going to be less than if we do the maximum of this. So these are all equivalent, okay? So now we're going to look at, okay, the fourth order Taylor polynomial at 1/4 minus f of 1/4 has to be less than or equal to, okay? And here's where the derivative, or the derivative, fifth derivative graph comes in, okay? We're going to do the maximum of this, right? So if you look at the maximum, we're centered at 0, okay? So I'm going to pull the graph up, and here's the graph, okay? That c value has to be between where we're centered at, which is 0, and 1/4, which is where we're finding the x value at. Okay, we're finding that 1/4. So this is 1/4 right here, because we go 1, 2, 3, 4. There's 4 lines, so that's 0.5. So this would be 0.25. So that's 1/4 right there. Okay, so the maximum value, okay, from 0 to 1/4 is right here, right? And it's really hard to read, right? Because this is 20, right in the middle is 30, a little bit more than 30, right? So it's really hard to estimate this, right? But if you go, okay, we're trying to get the maximum of it, right? And we want to show that the error is less than this. Well, if we pick 40 up here, okay, because definitely this value is less than 40, then we're overestimating the maximum, and that's going to be okay. All right, let's see if that works. Okay, so we're going to pick 40 because it's just an easier number to work with than trying to figure out what this number is right here, because that's going to be impossible to find. Okay, so let's use 40 for the maximum. So we know this maximum right here, okay, has to be 40, and I would say the absolute value of 40, okay, over 5 factorial, okay, and then times 1/4 to the fifth power, times 1/4 to the fifth power. And you know what? I should have put absolute value around that. Let me fix that. This shouldn't be a parenthesis, so it should be absolute value, because I'm taking the absolute value of each thing, right? Because just take the absolute value of the whole thing. We can take the absolute value of each thing. The absolute value of 1/4 to the fifth, I could just take the absolute value of 1/4. It would be the same number, okay? So absolute value of 1/4 raised to the fifth, okay? So this would be 40. So we know this has to be, I'm going to keep writing this. Taylor polynomial for 1/4 minus f of 1/4, okay, has to be less than or equal to 40, okay, and then 5 factorial, okay, that's 5 times 4, which is 20, times 3, which is 60, times 2, which is 120. So this 5 factorial is 120. Okay, and then times, all right, and then the absolute value of 1/4 is 1/4. Let me fix that. Okay, so absolute value of 1/4 is 1/4 to the 5th, so it'd be 1 to the 5th, which would be 1, and then 4 to the 5th, okay? So 4 times 4 is 16, okay? So 4 squared is 16, and because you can't use a calculator on this, okay? And 4 squared is, another 4 squared is 16, right? So 16 times 16 is 256, okay? So 16 times 16 is 256, okay? And then times another 4, right? Because then that would be 4 to the 5th. So 4 times 6 is 24, 20, 22, and 8, 9, 10, 10, 24. So 10, 24. Okay. All right. So now both these, we can reduce this, right? Because this would be 40, this becomes 1/3. Okay. So now we know that the Taylor polynomial at 1/4 minus f of 1/4 is less than or equal to, and this would be 1/3 times 1 over, not 10, 20, 10, 24, right? 10, 24. Okay. And then that would mean that the Taylor polynomial at 1/4 minus f of 1/4 is less than or equal to 1 over, okay, and this would be 3072. Okay. Now, we were trying to show that it's less than 1 over 3,000, right? Well, what do we know about 1 over 3072 compared to 1 over 3,000? This denominator is bigger than this one, right? So, okay, so that would mean that 1, so let's write an and, okay, 1 over 3072 is less than 1 over 3,000. Okay, so since this one's less than this, and this one is less than this one, therefore, it's fourth, right? No, therefore, okay, the Taylor polynomial approximation at 1/4 minus the actual function value at 1/4 has to be less than 1 over 3,000. And that's the work for part D. Okay, guys, like I said, this was a long video. I think it's almost 2 hours plus. Okay, it's like a movie. All right, So get some popcorn and watch this movie. Okay, and take breaks. Take breaks. Okay. All right, you guys take care. I'll see you for the next lesson. All right, guys, I forgot to do this. Okay, so what I want you to be able to do for this assignment, okay, is Taylor's theorem, Lagrange error bound. It's assignment 11.4, and I want you to do page 504, 1 through 9 odd, 11 through 14 all, and then 19 through 23 all. Okay, and that's for today, 325. Okay. All right, you guys, you take care. Bye.